Quantum mechanics is a fascinating phenomenon in quantum mechanics where particles interact, such that the state of one particle instantaneously affects the state of another, regardless of distance. When two particles combine, their properties combine. If you measure the position of one particle, you immediately know the position of the other, even if it is light years away. This behavior defies classical intuitions about locality and causation, making Albert Einstein's far-fetched work. The consequences of quantum entanglement extend beyond individual particles and may play an important role in understanding cosmic-scale phenomena. The work can provide information about the behavior of particles in extreme conditions, such as in black holes or in the early moments of the universe after the Big Bang. As the universe expanded rapidly in the early moments of its creation, bound particles could interact rapidly, creating correlations that shaped the distribution of matter and energy throughout the universe. In addition, researchers are investigating whether quantum mixing contributes to cosmic-scale structures such as the formation of galaxies or the distribution of dark matter. Some theoretical models may involve processes such as inflation, the rapid expansion of the universe, that may underlie the large-scale structure we observe. It shows how these connections can be fundamental to understanding not only microscopic quantum systems, but the vast contents of the cosmos. The study of quantum entanglement in relation to cosmic-scale phenomena also raises profound questions about the nature of reality. It challenges our traditional views of individuality and interconnectedness, suggesting that the fabric of the universe may be more interconnected than previously thought. When researchers explore these connections, they enter the territory where quantum mechanics and cosmology converge, inviting a deeper understanding of the universe and its fundamental principles. Quantum tunneling is a remarkable phenomenon in quantum mechanics where particles can pass through energy barriers that they would not have to cross classically. In the classical sense, a particle requires enough energy to overcome a barrier, and if it doesn't have that energy, it remains bounded. However, in the quantum realm, particles are described by wave functions, which correspond to the probability of being located. This inherent uncertainty allows particles to tunnel through barriers, emerging on the other side even though they normally do not have enough energy to overcome the barrier. To illustrate this, imagine a ball rolling with a hill in front of it. Classically, if the ball doesn't have enough energy to hit the top of the hill, it will bounce back. However, in quantum mechanics, the ball can appear on the other side of the mountain with a non-zero probability. This effect relies on the wave nature of particles and is most noticeable at microscopic scales where quantum effects dominate. Quantum tunneling has profound cosmic implications. For example, it plays a key role in nuclear fusion, which powers stars. In stars, hydrogen nuclei must overcome the Coulomb barrier due to their positive charge to fuse with helium. Quantum tunneling allows these protons to penetrate this barrier, allowing for coupling at different temperatures and energies. This process is essential for the production of energy in stars and directly affects the evolution of galaxies and the synthesis of heavy elements essential for life. In addition, quantum tonnage can provide information about phenomena such as cosmic inflation, the rapid expansion of the universe after the Big Bang. Some models suggest that quantum tunneling mechanisms could support the multiverse concept and create multiple universes. In this sense, tunneling affects not only individual particles, but also the creation and evolution of the universe. As our understanding of quantum tunneling grows, its cosmic significance reveals a deep connection between the fundamentals of quantum mechanics and the evolution of space. A quantum vacuum, often described as the lowest energy state of a quantum field, is an interesting concept in quantum field theory. Unlike the classical concept of a vacuum, the quantum vacuum is filled with activity. It is filled with virtual particles, which have become increasingly popular due to the uncertainty of quantum mechanics. These tiny particles exist for such a short time that they cannot be observed directly, but their effects can be felt by influencing various physical phenomena. One of the interesting aspects of the quantum vacuum is its role in energy conversion. These fluctuations create phenomena such as the Casimir effect, where two conducting plates in a vacuum experience an attraction due to the compression of virtual particles between them. This effect shows that the quantum vacuum can have measurable effects on physical objects, suggesting that empty space has no activity. The consequences of the quantum vacuum extend to the larger structure and evolution of the universe. In cosmology, vacuum energy is thought to be associated with dark energy, a mysterious force that drives the universe's acceleration. The energy density associated with the quantum vacuum can support this process, suggesting that the cosmic fabric has energetic properties that shape cosmic dynamics. As the universe expands, the quantum vacuum may play an important role in determining the formation and evolution of structures such as galaxies and clusters over space-time. In addition, the quantum vacuum may affect the early moments of the universe after the Big Bang. A rapid expansion called inflation can affect the high energy conditions that exist in the quantum vacuum, leading to the large-scale structure of the universe as we observe it today. Ultimately, understanding the quantum vacuum helps bridge the gap between quantum mechanics and cosmology, revealing how the fundamental properties of space and energy affect the history and structure of the universe. As we delve deeper into these concepts, we uncover the intricate connections that bind the fabric of reality together. Quantum mechanics and general relativity represent the two main pillars of modern physics, but they operate on very different principles. Quantum mechanics describes the behavior of particles and their interactions on very small scales, and general relativity describes gravity as the curvature of time caused by mass and energy on cosmic scales. Reconciling these two theories has proven to be one of the most important problems in theoretical physics. On cosmic scales, gravity primarily occurs in regions where gravity is unusually strong, such as black holes or the very universe. In these situations, the assumptions of general relativity break down, leading to a singularity where the laws of physics work as we know them. Quantum mechanics allows for uncertainty and probabilistic results that are not easily reconciled with the deterministic nature of general relativity. This dichotomy suggests that a more comprehensive framework is needed to integrate these two domains. The pursuit of a quantum theory of gravity seeks to bridge this gap. Several approaches are studied, including string theory and cyclic quantum gravity. Line theory states that the main components of the universe are one-dimensional lines rather than points, allowing us to describe gravity and other fundamental forces within a single theoretical framework that accommodates both quantum mechanics and the geometric nature of space-time. Tao. At the same time, loop quantum gravity attempts to calculate itself, which consists of discrete spatial structures that can resolve singularities and provide a coherent description of gravity at the quantum level. Furthermore, concepts such as the information paradox associated with holography and black holes challenge our understanding of information and its conservation in quantum mechanics. The holographic principle suggests that information in the volume of space can be represented as a theory that resides within the boundaries of that space, bridging local and non-local concepts. As researchers explore these and other avenues, there is hope that a deeper understanding of quantum mechanics and general relativity will provide a unified view of the universe that spans both minuscule and cosmic scales. This reconciliation promises not only to deepen our understanding of fundamental physics, but also to shed light on deep questions about the nature of reality. The idea that quantum effects can create connections between distant parts of the universe, or even separate universes, arises from unique principles of quantum mechanics, particularly quantum entanglement and non-locality. In quantum mechanics, entangled particles maintain correlation, meaning that a change in the state of one particle instantly affects the state of the other, regardless of the distance separating them. This phenomenon raises interesting possibilities for how information and influence can travel across spatial distances. Quantum particle interactions challenge traditional local concepts by showing that they extend beyond familiar spatial boundaries. Some physicists hypothesize that this information or influence can be transmitted over long distances, unconstrained by relativistic limits, such as the speed of light. This concept leads to interesting debates about the nature of spacetime and causation, which raises the question of whether it can serve as a mechanism of extensive communication within the universe. In addition, quantum mechanics can provide a basis for the interrelationships between these realms, rather than the concept of a multiverse with multiple universes with different physical laws or constants. In some interpretations of quantum mechanics, such as the many worlds explanation, each quantum event creates a propagation of reality. This suggests that there may be interactions or connections between these industries, potentially influencing the universe. These interactions may produce observable effects, although their detection remains an important challenge. It should also be noted that there are theories that propose mechanisms that can influence spatial structures. For example, some researchers believe that quantum entanglement may have played a role in the coordinated behavior of particles and fields in the early universe. This may help explain phenomena such as cosmic inflation or the uniformity of the cosmic microwave background radiation. Although these concepts still face many challenges in terms of theoretical and empirical verification, they represent profound implications for quantum mechanics. They invite exploration into the fabric of reality, urging us to rethink the structure of the universe and its potential connections. As the dialogue between quantum physics and cosmology develops, these ideas may pave the way for a unified understanding of the cosmos. Negative mass is a hypothetical concept that appears in some theoretical frameworks within physics. It refers to the shape of a mass in reaction against the forces acting on it, compared to a simple positive mass. For example, if a particle with a negative mass were to be pushed, instead of accelerating in the direction of the applied force, like a positive mass, it would accelerate in the opposite direction. This consistent behavior defies our usual understanding of mass and forces in classical and relativistic physics. In theory, negative mass can lead to strange and complex scenarios. For example, if negative mass is present and interacts with positive mass, it can create unique dynamics. A classic thought experiment involves a scenario where positive mass attracts negative mass. In such a case, the negative mass can accelerate towards the positive mass, and the positive mass can move away from it. This can lead to a runaway effect, where the system can amplify itself indefinitely, raising questions about stability and causality in physical systems. The implications of negative mass extend to debates about gravity and cosmology. Some scientists speculate that if the universe has negative mass, it could affect the dynamics of cosmic structures, possibly explaining phenomena such as dark energy or the acceleration of the universe. Integrating negative mass into our understanding of gravity could redefine the concepts of gravity and repulsion, potentially leading to new insights into the nature of cosmic forces. However, it should be noted that negative mass has not been detected or observed in empirical experiments to date. Although some theories in general relativity and quantum field theory accept the concept of exotic matter, the materialization of negative mass remains speculative. Nevertheless, studying the theoretical framework of negative mass helps broaden our understanding of the behavior of the universe and influences the search for a more complete understanding of fundamental physics and cosmological phenomena. Indeed, the possibility of forms of matter different from what we observe is an active area of research in theoretical physics. Although we are familiar with simple matter composed of atoms, composed of protons, neutrons, and electrons, There is reason to believe that the universe could harbor exotic forms of matter with unique properties. One such example is dark matter, which is thought to make up about 26% of the mass energy of the universe. Dark matter does not interact with electromagnetic forces like ordinary matter, i.e., it does not emit, absorb, or reflect light. This means that it remains invisible, only detectable through gravitational effects on visible matter such as galaxies. While the exact nature of dark matter remains elusive, leading candidates, including weakly interacting massive particles and axons, would both have properties and interactions that differ from those of ordinary matter. In addition, researchers are exploring the concept of exotic matter, which may include matter with negative mass or an unusual state configuration. For example, some theories propose the existence of quark matter, in which quarks, the basic constituents of protons and neutrons, exist in a free state without being constrained by standard atomic structures. This phase of matter can exhibit properties that are very different from what we experience every day. Another interesting category is supersymmetric particles that arise in supersymmetry theories. These hypothetical particles would have unique properties, be heavier than known particles, and interact with forces differently. If discovered, they could change our understanding of fundamental forces and particles. The study of these forms of matter invites speculation about the nature of the universe and its potential configurations. It challenges our traditional views and encourages scientists to look for new physics outside the standard model. The exploration of exotic matter not only expands our understanding of nature, but also opens up questions about the fundamental principles that govern the universe and the potential for phenomena beyond current observational capabilities. As researchers delve deeper into these mysteries, they come closer to answering deeper questions about space and our place in it. Mirror matter is an interesting theoretical concept that suggests the existence of a parallel form of matter that resembles ordinary matter but has opposite properties. The idea arises from some extensions of the standard model of particle physics, particularly those related to parity. Parity in physics refers to the symmetrical nature of physical processes. The laws of physics must remain unchanged when spatial coordinates are reversed. However, when the pairing is broken, as seen in the weak interaction, it leads to interesting speculations about the existence of a mirror counterpart to ordinary matter. In this network, the mirror material will consist of particles that reflect the properties of familiar particles such as electrons, protons, and neutrons, but with opposite interactions and potentially different charges. For example, mirror electrons can interact with mirror protons to form mirror atoms, creating a parallel universe of mirror matter. One of the remarkable properties of mirror matter is that it will not react strongly with ordinary matter under normal conditions, making it difficult to detect. This lack of interaction suggests that it coexists with our universe without being observed. Interactions between mirror matter and ordinary matter are likely to be rare, if real, primarily through very specific interactions via gravity or hypothetical intermediate particles. This concept raises interesting and complex questions about the nature of our universe. For example, if mirror matter contributes to dark matter, its gravitational effects may occur through electromagnetic interactions without being detected. In addition, some theoretical proposals suggest scenarios where mirror matter could explain cosmic phenomena, such as the observed asymmetry between matter and antimatter or the nature of dark energy. Alternatively, interactions with mirror matter can potentially lead to observable results in high-energy particle collisions in accelerators or extreme astrophysical environments. While matter remains a speculative concept without empirical confirmation, it offers a tantalizing way to study the nature of the universe and prompts a deeper investigation into the fundamental forces that govern our reality. As researchers continue to explore these ideas, Interactions between our familiar universe and potential mirror counterparts may illuminate new aspects of fundamental physics and space. The concept of entire galaxies or cosmic structures composed of exotic matter is an intriguing and speculative idea that stems from the expansion of our universe. Exotic matter refers to hypothetical forms of matter that have unusual properties that differ from normal matter. Exotic matter includes theoretical forms such as negative mass, quark matter, and even mirror matter. While we have yet to directly observe such materials, the thought of their potential existence opens up interesting possibilities for the nature of space structures. If exotic matter is present, it may influence the formation and evolution of galaxies in unique ways. For example, consider a galaxy with negative mass. In theory, such a galaxy could have a completely different arrangement than typical galaxies, as particles with negative mass would resist gravity. This interaction can have a repulsive effect, possibly forming large structures that spread out rather than collapsing under gravity. Such a formation would challenge our current understanding of galaxy dynamics and stability. Moreover, the existence of exotic matter may provide alternative explanations for current mysteries in cosmology. For example, if a fraction of dark matter should be composed of exotic matter, this could help explain the discrepancy between observed gravitational effects and predictions from standard models of galaxy formation. Exotic matter, such as quark matter, can behave uniquely under extreme conditions, possibly affecting the rate of star formation or the distribution of matter within a galaxy. Moreover, if we expand our view beyond individual galaxies to consider larger cosmic structures, the interactions between ordinary and exotic matter can have surprising consequences. For example, a cosmic web formed by a mixture of exotic and normal matter may exhibit unusual properties, affecting the expansion of the universe or creating new interactions with gravitational waves. While the idea of galaxies made of exotic matter remains in the realm of speculation, it expands our understanding of cosmic formations and encourages researchers to explore unusual avenues of theoretical physics. Exploring the potential consequences of exotic matter invites us to reconsider the fundamental properties of the universe, revealing hidden complexities that could change our view of galaxy formation and cosmological order. As knowledge of fundamental physics grows, the idea of such exotic structures may resonate within the broader space exploration framework. Exotic forms of energy, such as dark energy, play an important role in the evolution of the universe. Dark energy is a mysterious force that makes up about 70% of the universe. It is responsible for the rapid expansion of space. As the universe continues to expand, the influence of dark energy becomes increasingly important, further separating galaxies and shaping the large-scale structure of the universe. The presence of dark energy changes the dynamics of cosmic evolution. The early universe was dominated by gravity, which formed matter into structures such as stars and galaxies. However, as dark energy becomes more visible over time, it resists gravity, causing an expansion that appears to accelerate. This has profound implications for the fate of the universe, affecting the interactions and eventual evolution of galaxies and clusters over billions of years. In addition, other exotic forms of energy may affect the universe in different ways. For example, ideas about modified theories of gravity may not yet be fully understood. Such theories can influence the behavior of dark energy and the formation and evolution of structures. Although dark energy is the most studied, the universe may hold other surprises waiting to be discovered, deepening our understanding of cosmic evolution. Understanding these exotic forms of energy challenges not only our view of the universe's past, but also our notions of its ultimate fate. Will the expansion continue indefinitely, leading to a cold and desolate universe? Or can we discover new forms of energy that can change this trajectory? The answers to these questions will change our understanding of space and its continuous journey through time and space.